Dear students, in this talk we will discuss elastic properties of beams. Beams are very important construction elements. Every building has a beam, pillar. In the construction of those beams, civil engineers have to calculate moment of force. They use concepts of Young's modulus, rigidity modulus, moment of inertia. All these concepts are required to estimate the force they experience, the beams experience, what is the moment of force, what is the torque, all this. So, in this talk, we will discuss bending moment, moment of force. What is bending moment? Let us consider the most common construction element, a beam. A beam has greater length when compared to breadth and height. I can call this as a beam because for this structure, length is very much greater than breadth, length is very much greater than height. So this qualifies to become a beam. This kind of beams withstand lot of load, stress in a construction structure. For example, if this beam is fixed here, then this becomes a single cantilever. It's a beam fixed at one end, loaded at the other end. This is a single cantilever. Suppose if it is fixed at both ends, you can call it double cantilever. Okay? So now, what happens when a beam like this is acted upon by a stress? I will give you an example. Look at this beam. Imagine this to be a beam. Okay? If I call this as A, B, C, D. See, imagine this to be a beam. A, B, C, D. Now, suppose I exert a force on it. See here, when it bends, now it is bending. Please observe, below this central portion, these layers below this central axis are expanding. Okay? These layers are expanding, whereas layers above this, in this portion, you see contraction. Correct? Some layers are expanding, some layers are contracting. This layer which is not changing is said to be neutral axis. Correct? Now, I will draw it here. I will draw this figure here and show you the neutral axis. So, when this is bent, it looks like this. See here? Okay? What I have to notice is a layer in this beam does not get affected. That layer is called as neutral axis. This layer will not experience any change. Okay? So I call this as neutral axis. Correct? Now, this layer in this diagram is experiencing expansion, elongation. Correct? Whereas this layer below the neutral axis here in this diagram is experiencing contraction. So now a restoring force is set up inside this beam. Due to its elastic nature, external force is trying to push this layer outwards, push this inner layer inwards. But now, as a response to this applied stress, a restoring force will be set up inside this. Okay? Now, the moment of this restoring force is called as bending moment. The moment of the restoring force set up in a beam experiencing a stress is called as bending moment. Now we have to find an expression for this. What is bending moment? What is the formula for it? It is easy. Now let us find radius of curvature of this axis that is bent. Okay. Now I'll take a portion, I'll call this as PQ on the neutral axis. Okay. Let the section PQ subtend an angle theta at the center. Okay. Let R be the radius of curvature. Now what I will do, I will take a section, another layer above neutral axis at a distance z from this. Okay. Now that layer has got deformed. Neutral axis has not undergone deformation, no change in its length, but this layer is above the neutral axis at a distance z. So that has undergone the deformation. See this? Now this becomes P prime Q prime. Correct? Before the application of the stress, all the layers had same length like this. Correct? Length was same for all the layers. But now, due to the application of the stress, this neutral axis is not deformed. I am considering a small length on neutral axis PQ subtending an angle theta. Now if you take another section P prime Q prime at a distance z, so this is its new length. Now the difference of this length and this length is called as strain. That gives us the longitudinal strain. So in this case we can calculate strain is nothing but P prime Q prime minus PQ. Okay. So P prime Q prime is R plus Z into theta. Correct? How do I write this? I used this in the previous lecture also. Suppose if this is theta, this is S, this is R. S is equal to R into theta. In our case now, this is P prime Q prime. Correct? Similarly, what is PQ? PQ is R into theta. Correct? PQ is this. Correct? This is R plus Z. So now simplify this. Z theta is strain, change. Okay. Now what is linear strain? Strain is change in dimension by original dimension. So change is Z theta. Original dimension is PQ, that is nothing but R theta. So Z by R is strain. Okay. So now I need bending moment, force. So I will write the expression for Young's modulus, which involves stress, force and strain. We will evaluate what is bending moment. Okay. Remember this strain. Now next is simple calculations. So now Young's modulus of elasticity, Y is equal to longitudinal stress by longitudinal strain. Correct? Now stress is forced by A. A is area of cross section of the element beam. Next, strain is Z by R. Correct? This is Y. Now I need moment of force. So first let us take force. Force is equal to Y into A into Z by R. Correct? This is force. Now, what is moment of this force? Moment of force is nothing but force into distance. Z is the distance between the two layers. Therefore, it is Y A by R Z square. Correct? Now I want total moment. Total moment in the beam. So I take out this constant and take summation of area Z square. You know what is this element called as? This term is called as geometrical moment of inertia. Geometrical moment of inertia. I am using the word moment of inertia, which you have been hearing in mechanics chapter. Moment of inertia for a material represents mass distribution in a material. Two objects of same mass but of different dimensions will have different moment of inertia. Moment of inertia depends on the axis about which we are considering. Moment of inertia has different types. Geometrical moment of inertia is area into length square. This is called as geometrical moment of inertia. Okay? Now, this is total moment. Now, I take an example. For example, if I take a beam with rectangular cross section, what is moment? If I take a beam with circular cross section, what is a moment? This derivation is important in the exam for solving numericals, for rectangular cross section, for circular cross section. So now I take bending moment for rectangular cross section. Case 1. If the beam is rectangular cross section, then geometrical moment of inertia is given by Az square. A will be length, breadth into thickness, area. Z is called as, it has dimensions of length square, radius of gyration. What does it mean? For a rectangular, this is thickness square by 12. This can be derived. Okay? Now, substitute this here. Therefore, bending moment will be Y by R into B dq by 12. Correct? Ig is written B into d square dq by 12. Now, second case, circular cross section. Case 2, if the beam is of circular cross section, then Ig, geometric moment of inertia, is Az square, area is pi r square, Z square is radius square by 4. Okay, this is Z square. Z has got length, dimension of length. It is called as radius of gyration. Now, therefore, bending moment is Y by R into pi r square, pi r to the power of pi r 4 by 4. Correct? So, this is the expression for bending moment for rectangular cross section. This is for circular cross section. Now, once we know this, now is the time to understand the real problem in engineering, civil engineering. The problem with single cantilevers. How to find depression of single cantilever? What is the amount of depression in a beam? Because you have done a lab experiment in physics lab. That experiment is Young's modulus. You have taken a beam, you have put loads on both sides, and you have studied the depression or elevation. For civil engineer, this is very important. Imagine a bridge supported at two ends. That is a double cantilever. Now when it is loaded, what is the depression or the elevation? This is a very important problem. So we will now take up single cantilever problem. We use this formula for studying single cantilever that is loaded. Okay. So we will be calculating now depression in the case of single cantilever. Expression for depression that is produced in a single cantilever that is loaded. What is single cantilever? It consists of a beam. See this? It consists of a beam. This beam is fixed at one end. Okay? A single cantilever is a beam. Beam means its length is very much greater than thickness and breadth. It is supported at one end. It is loaded at the other end. For example, let AB be the beam. Okay? I put a scale pan here and apply load here. Okay? Load is omega, mg. When this is loaded, it gets deformed. It takes this shape. Correct? It bends. Now, what is the depression produced? To calculate the net depression, we will use the concept of bending moment. I will take a point at a distance x from the point A. Okay? Let the length of this beam be L. Okay? So I take a point P at a distance L minus x. Correct? This is point P. Now I take a very closely spaced another point Q. Correct? These two are very close, separated by a distance dx. Now suppose if I draw a tangent from P and tangent from Q, they differ like this, they look like this. Since these two are very close, this looks like this. Okay? I am drawing two tangents from P and Q. Now if P and Q subtend an angle d theta, this angle also will be d theta, correct? Please understand this. P and Q, if they subtend an angle theta, d theta at the center O, radius of curvature is R, then I have drawn tangents from P and Q which are very closely spaced. The separation between these two tangents is d theta. So this is the very small depression from P to Q. I have to find depression from here to here. Correct? So depression produced between P and Q is this due to this load. Correct? So now B prime will be the final position of B. Now using expression for bending moment, we can arrive at an expression for total depression Y. So first let us begin the moment. Bending moment at x is load applied into distance. This is the basic expression for bending moment. Force into distance is moment. Okay? Now, this is also equal to, we have just derived in the previous y by r into geometrical moment of inertia. Correct? So this is equal to y by r into area into k square or z square. Z is radius of gyration. Right? Now, the next step is we will take the expression for 1 by r. Look at this triangle OPQ. From triangle OPQ, correct? See here, PQ is equal to r d theta. Right? From this triangle, PQ is equal to r into d theta. To substitute for 1 by r, what I do is 1 by r is equal to d theta by PQ, that is dx, d theta by dx. Distance between P and Q, let it be dx, very very small. Correct? So now I substitute 1 by r here. Right? So bending moment will be y area z square, 1 by r is d theta by dx. Correct? I have replaced for 1 by r. Now we also, if I draw this diagram again, see this? This is the support, this is the beam. Now it has bent like this. Correct? The point P, Q is this. This is R. PQ is very small, separated by distance dx. Now the depression from P to Q is here, y. Correct? This angle is d theta. If this is d theta, this angle is also d theta. Right? Now from this diagram, dy, let this be dy, is equal to this distance. What is this distance? L minus x. This is L, this is x. Point P is at a distance x from the support. Dy is equal to L minus x into d theta. Correct? Therefore, now I substitute for d theta from this here. L minus x into, this was W equal to into L minus x. Correct? So in this expression, what is d theta? From 1, d theta equal to omega into L minus x into dx by y a z square. Correct? Now substitute 2. This is expression 2 in 1. Is this alright? Here, this is 1. Therefore, depression due to load omega at point P, okay, is now L minus x into omega into L minus x. L minus x into d theta, okay. So d theta is this, dx by y a z square. Correct? Yes. Now So I'll just simplify this. Omega into L minus x whole square dx by y a z square is elementary depression. Now I need total depression. For that I have to integrate from 0 to L. Okay? Total depression. We call it small y. This is small y, not capital Y Young's modulus. Okay? Is equal to integration y a z square into L minus x whole square dx 0 to r. Correct? So now let us integrate that. Now when you integrate it, total depression is integration of dy. So this will be y, omega is weight, y a z square. So this will be L square dx minus x square dx 0 to L minus this is plus a square plus b square minus 2lx dx 0 to r. So omega y a z square L cube by 3 plus is also L cube by 3, is it? Is it correct? L square, already this is x, okay, minus